Hello friends, Namaskar. We are now in the 7th module of the course, and in this 7th module, that is the 5 lectures will be devoted on various aspects of dehydrated and snack food products, particularly those which are prepared from fruits and vegetables. So, in today's lecture, that is lecture 31, we will discuss drying techniques and equipments that are used for preparation of dehydrated and snack fruits and vegetables products. The we will discuss the concept of drying of fruits and vegetables, particularly what are the methods and equipment that should be used for dehydration and drying of fruits and vegetables, because these fruits and vegetables they have very heat sensitive components and bioactives, etc. So, the traditional methods of drying may not be much suitable or much useful as far as the quality of the product is concerned, or retention of bioactive and other micronutrients are concerned. So, we will discuss only those methods and technologies for drying of the fruits and vegetables, which may be beneficial from the quality point of view. So, the methods and equipment used here will include hot air flow drying, fluidized bed drying, microwave, radio frequency, infrared drying, pulse vacuum drying, and finally refractive window drying, foam mat drying, etc. So, let us see what is the main purpose of drying and dehydration of fruits and vegetable products. In the picture you are seeing various products which are available in the market. So, obviously, in the earlier classes also, when we were discussing the preservation principles, there we discussed preservation of food by addition of heat or removal of moisture, and there the drying and dehydration mainly is to reduce the moisture content of the material to the desired level. Okay. So, what is done here? Obviously, there is a dryer in which the prepared fruits and vegetable is put into the dryer, where from some suitable source heat is supplied. So, this heat causes the evaporation or removal of moisture, and finally, we get the dried fruit or vegetables. So, in general, the heat supply sources may be conduction, convection, internal generation of heat through microwaves, radio frequency, etc., or even the surface radiation like sunlight, or a combination thereof from various methods. Okay. So, in this process flow, I have just tried to give you a general scheme of fruits and vegetable drying. So, obviously, the raw fruit or vegetable is after subjecting it to the obvious pre-treatments like sorting, washing, peeling, coring, etc., that we have discussed in earlier classes, then it can be subjected to two major treatment depending upon the what is the in which form, what is the nature of the dried product, whether you want the dried product in the form of slices, cubes, and such other form, then this material may be grinded, crushed, directed, and then it is put into the like slicing, cutting, or particle with whole fruits and vegetable, etc. So, again these pre-treatment are given, peeling, cutting, slicing, etc., and then it is subjected to some sort of drying process, which we will discuss little later, and finally desired and up to final product. Other may be that if you want to convert it get the material into the form of fine powders, etc., then it may be material after pre-treatment, it can be ground or crushed. All right, you may get juice and pulp, and then juice and pulp may be dried into the form of powders or flakes. Okay. And then again all these dehydrated products obviously has to be properly packaged, so that, and packaging aspect earlier about the whole fruits and vegetable, cut fruits and vegetable we have discussed, and packaging of the processed product we will take up separately in another module. So, this is the, so in the today's lecture we will discuss the drying technologies, mainly concentrate on the dehydration in the form of cubes, slices, chips, etc. But a few technologies also we will include those which can be made to prepare powder. However, although they for a powder preparation technology there is a separate lecture, that is which we will take next lecture. So, for the dehydration, that is conventionally or traditionally used method for drying of fruits and vegetable is hot air flow drying. Okay. As I told you, it is done to enhance storage stability, to minimize packaging requirement, to reduce transportation cost, etc. You can see here in this figure here there is a drying chamber, and in this drying chamber the air which is circulated through some sort of heater, that is heated air is pushed into the drying chamber, and in the drying chamber pre-prepared product either in the form of thin slices, thick slices, in the form of the cubes, triangle, whatever shapes etc. material, prepared material is there. So, obviously, the evaporation of moisture takes place. Okay. So, there are three important things which need to be controlled, that is the controlling process parameter in the hot air flow drying include temperature, that is temperature of the hot air, that is the flow rate of the air, humidity of the air, and also that the thickness of the material, form of the material, also material properties also. So, that is let us discuss little bit heat and mass transfer related. So, as I told you, that is here in the drying chamber, that is in one case it is heat is flowing here, okay, and the material that is which was initially from the at a T1 temperature, it is put into the dryer, that is its temperature is raised to T2 with the help of the heated air, and then the moisture goes out. Okay. And also in the drying chamber some insulation is provided, so that there is no heat loss. So, water on the surface of the material is dried by hot air flow. Moisture migration and heat transfer due to temperature difference occur in the opposite direction, as you can say heat is flowing from outside to inside and moisture is going from inside to outside, because the material is there inside. So, when the moisture content in the external part is lower than that in the internal part, water diffuse from high moisture region to low moisture region. At the same time, the temperature in the external part is higher than that in the internal part. Thus, it creates a temperature difference, and which facilitates the moisture removal. Control of heat and moisture transfer is essential to preserve the quality of the dried vegetables and fruits, as I told you earlier also, because these materials the fruits and vegetable contains heat sensitive components, micronutrients, etc. So, they should be preserved. Okay. Regarding mass and energy balance in the drying, that is mass balance is taken as a water entering the dryer and water leaving the dryer. Okay. That is water in is equal to water out. So, if that is a air flow rate, that is mass of the air, that is MA is entering into the dryer, okay, its H2 is the absolute humidity of the air entering the dryer, and HA2 if it is the energy content of the air entering the dryer, okay, that is HA2, okay, and air out HA1 is the energy content of the leaving the dryer, leaving and okay. Then using similarly, that is the product in, it is a certain amount of the product MP is going, its X1 is the initial moisture content in the product, and HP1 is its energy content entering the product. So, you have the mass of the product, okay, initial and final moisture content and energy content, whatever is entering. So that you, and then accordingly what is the leaving out, mass of the product leaving, energy content of the product leaving, and moisture content which is remaining in the product. So from these information one can calculate MA H2 plus MP X1 equal to MA H1 plus MP X2. So from this equation you can get the mass balance or water balance. Similarly, that if you have MA HA2 plus MP HP1 is equal to MA HA1 plus MP HA2 plus Q, where is Q is the energy lost to the surroundings. Okay. That is in the figure you can see that energy is going, Q amount of energy is going out to the surrounding. So from these equations you can have energy balance as well as mass balance. Water in is equal to water out is the mass balance, energy in is equal to energy out is the energy balance. Also you can have the find out the enthalpy of the air and enthalpy of the wet solids. You can use these equations like HA is equal to CS TA minus T0 plus H lambda 0. Okay. Where H is the enthalpy of the air, CS is the humid heat of the air, and then TA and T0 are the temperature of the air or temperature of the reference temperature. Lambda 0 is the latent heat of water at T0 degree Celsius, and H is the absolute humidity. So from these if you have this information you can find out enthalpy of the air as well as the enthalpy of the wet solids. Okay. This is the schematic shown for the various hot air drying equipment, that is the box type vegetable dryer. These are the arrangement from the where the hot water is going and heating the air, and the dryer product is kept and the heat goes and moisture goes out. That is the box type vegetable dryer. Another is the multi-layer air dried vegetable dryer, where you can see these are the products are shown, that is they are one above the other layer. The product is loaded into the drying chamber in different layers one above the other, and of course there is a sufficient gap between the layers so that the hot air steam, that is hot air is going. So air flows through, it goes above the, so heated air goes above, and finally humid air outlet channel is provided. Through this outlet channel humid air goes out, or in some cases it is recirculated, the recirculatory air dryer, that is the air it is coming out, it is again heated and used. This and the mesh belt air dried vegetable dryer, AD vegetable dryer, where it is the conveyor belt. So in this conveyor belt the principle is again the same, that the material through this hopper the material is conveyed into this dryer and then it moves. Okay. And where it comes in contact with hot air and the moisture leaves out of the surface, and finally that the dried product is delivered on the other end of the equipment. Okay. Then fluidized bed dryer, this with here with the action of mechanical vibration and hot air flow, the weight of the material is balanced in a fluidized state. So basically here in the it is some sort of, that is the little advancement of the hot air drying, where the material is kept in the fluidization state, and this advantage of this system is that airflow with the high temperature and low moisture content achieve high drying rate and energy efficiency. Okay. And also it requires low capital investment and is easy to maintain, it is easy to control and uniform drying, because the heat can be, that is it is material is fluidized in the, so heat transfer is increased, you get a better, and this is used for the drying of the granular vegetables such as potato dices, apple dices, carrot dices, even the small material like pea, etc. So those particularly which are the smaller size material which can be easily fluidized, kept in the fluidized state, they can be used in the fluidized bed dryer. So it is a better technique from the quality point of view. So the parameters affecting the air drying, they may be physical parameter like pre-treatment, that is the blanching. We have earlier discussed details about the blanching because it is necessary to inactivate the enzyme. If the enzymes are not inactivated, it may cause the browning and other problems during the drying process with the activation of the heat. So, it can be either physical treatment or even chemical treatments also are given sometime, depending upon whether it is a fruits and vegetables is tried, like for sulfur dioxide treatment, that is in the form of KMS, the potassium metabisulfite used. So, basically it is the sulfur dioxide treatment is given to control both enzymatic as well as non-enzymatic browning reactions. Certain metal ion treatment like cupric and zinc ion are used for protecting green color in the vegetables, etc. So, these metals ions, when they are used, they complex with the chelates, that is they form chelate, and which protects the color of the vegetable, green color, etc. Also, that is salt and alkali treatments are used which inhibit enzymatic browning, and also it improves the structure of the rehydrated vegetables. Okay. So, the factors which influence the airflow drying are obviously the temperature. Higher the temperature, there will be more better drying rate. High temperature difference between the product and air increases the rate of dehydration. Similarly, air velocity or air flow, all right. If air velocity is high, there will be more rapid removal of moisture, and vice versa. Humidity, low air humidity, air can absorb more moisture, and vice versa. Even the pressure at constant temperature, if pressure is lowered down, the boiling temperature decreases, and with increase in the rate of moisture removal, and that is the lower pressure means that if you create vacuum. So, hot air vacuum drying, this is the principle of that. Also, then there is other methods is used, dielectric drying. The dielectric drying here, it is used as I told you in the beginning, that since these fruits and vegetables, they contain heat sensitive components, etc., where that are bioactives, etc., which the danger is there, these can be degraded, their quality can be degraded, etc., if the excessively high temperature is used in the drying. So, novel methods of drying have proven better in this effect. There is one, that dielectric heating. Here, dielectric energy is used for the removal of water. Okay. So, dielectric energy absorbs when it is there in the material. So, either there is a dipolar relaxation or ionic conduction. So, dipolar relaxation means that when water molecule attempt to follow the electric field as they rotate at very high frequencies, and such rotations of the water molecules produce heat, which is expressed as a dipolar relaxation. In the ionic conduction principle, there are ions such as those present in the salty food migrate under the influence of the electric field. They cause friction, and because of this friction, heat is generated. Okay. So, both the electric constant and the dielectric loss factor can measure the ability of the material to interact with the electric field, and there are two types of the dielectric drying, are microwave drying and radio frequency drying, and both these methods are becoming very popular nowadays for the dehydration of fruits and vegetables. So, microwave drying, okay, it uses the frequency of electromagnetic waves in the range of 300 to 3000 megahertz. Microwave heating is caused by the ability of the material to absorb microwave energy and convert it into the heat. So, basically it is the dipolar and ionic mechanism. In the earlier class we have discussed this detail. Okay. So, it causes volumetric heating of the material. So, it has advantages like achieve faster rate of drying, improve quality of some foods by reducing the shrinkage, and also combining with the other method to prove efficiency. In the next slides we will discuss this aspect. That is, one can have that microwave drying can be combined with other dryings. However, there is also some disadvantage, that is, one has to control the, because this the temperature can go very high, so excessive temperature can cause scorching of the products, and there may be off flavor development, etc. Even rapid mass transfer can cause puffing, okay, which might be undesirable for some products. So the microwave energy which is given in the drying, this must be properly controlled, so that the temperature does not. This is the schematic system giving a continuous microwave dryer. Okay. So this is the feed bins, that prepared material, fruits or vegetable in the form of slices, cubes, etc. They are through this help of the conveyor belt, they are put into the sent into the microwave dryer, that is drying chamber, where there are some magnetronics, etc. are suitable capacity are provided, which gives the microwave. And these here, you can see here that is in this, the product is exposed to the microwave. So product absorbs the microwaves, and finally that we discussed in the earlier slide, there is due to molecular flux movement, etc., internal heat is generated. So heat goes out of there is a dehumidification pipeline is given, and some suitable arrangement in the system is given to take out the moisture, water vapor from the system. Okay. And then finally the dried material comes, and a proper suitable after locking arrangement, that is entry lock and exit lock provided in these things. Okay. So this is schematic. Then as I told you that microwave, it can be combined with the air drying or with the vacuum drying to improve the efficiency of the process. That is, hot air drying is combined with microwave heating in order to enhance the drying rate, and microwave heating can be combined with the hot air in 3 different stages. Like in the stage 1, microwave heat is applied at the beginning, and which because of that interior gets heated very rapidly. So in the earlier normal conventional drying, there is a heat, that the time delay, that is the conduction, etc. The problem that can be avoided here with the application of microwave. The material, interior of the material can be rapidly heated. And then in second stage, the microwave heating creates a porous structure which can further facilitate the mass transfer of water vapors. And finally, that at the final stage of drying, toward the end, this microwave, that is drying rate, when the drying rate begins to fall, microwave heating vaporizes the moisture and forces it outside. So it improves the efficiency of both normal air drying as well as vacuum drying process. Okay. These are the schematic that is, you can see, that is here the normal microwave assisted fluidized wet drying, that is the fluidization is kept, and in this where that is hot air is given for the fluidization, at the same time some arrangement is there with the control panel where you can expose it to the microwave, desired microwave. So and there is the microwave assisted tunnel dryer, that is the tunnel dryer you have seen. So hot air is going on, and this also is given the microwaves schematic arrangement. Then radio frequency drying, like microwave, radio frequency waves are part of the electromagnetic spectrum. The difference in the frequency range. Radio frequency treatment involves heating with electromagnetic waves, and at frequencies such as 13.56 megahertz, 27.12 megahertz and 40.68 megahertz. Radio frequency drying is a volumetric heating method where electromagnetic waves directly couple with the food to generate heat. However, there are certain challenges like non-uniform heating and runaway heating, which cause overheating in corners, edges and center parts, especially in the foods of intermediate and high water content. So these care has to be taken properly, control properly. It is a radio frequency assisted air dryer, and in this various, that is arrangement are there, like these are the 2 electrodes here, bottom electrodes and upper electrode. The material is kept here, and this are heated with the help of conveyor belt. The material is coming, okay, hot air, that is and there is a provision for supply of hot air, and then at the same time when it comes, then radio frequency waves are provided, that is okay, and hot air is distributed in the chamber, and this is facilitated by radio frequency drying, that is with the help of. So, obviously, the drying rate is enhanced. These are the different components which are provided in the system. Okay. Then infrared drying, that is it is portion of the electromagnetic spectrum which falls between the region of visible light and the microwaves, that is called infrared. So, when electromagnetic radiation impinges on the food surface, it causes changes in the electronic, rotational and vibrational states of atoms and molecules. So, after penetration in the food materials, infrared rays vibrate the constituent molecule at a frequency of around 60,000 to 150,000 megahertz, and which results in intermolecular friction and brings about rapid internal heating. And this is because of the OH bonds in water absorb the infrared radiation energy and rotate with the same frequency as the IR radiations. Okay. These are the different arrangement. Again, schematic, that is simple infrared drying, that is the sample tray, and it is provided, the chamber is provided with an infrared lamp. Okay. So, it is infrared heating. Then infrared assisted hot air drying, that is the same infrared lamp chamber where some additional supply of hot air in and hot air, cool air out. So, it further again it will give a better result. Infrared assisted vacuum drying, that is along with this supply, that is also chamber is provided with a vacuum pump, and which that pressure is reduced and which can cause the facilitate the vaporization at a lower temperature. And then infrared assisted freeze drying. Okay. So, the freeze drying principles, all right, that is the sample tray is here, and it is the lower temperature condensers that are provided to reduce the temperature to -23 or -50 degree, whatever is there. So, that is, and then infrared lamp is provided. So, both facilitate, that is okay, removal. Then pulsed vacuum drying. Pulse vacuum drying is another technology. It is a novel drying technology which uses successive changes of vacuum pressure in the drying chamber to enhance moisture transfer during drying process. So, instead of continuously having the same pressure level, one can have that progressive, that is the pulse in the form of, okay, during the PVD operation, the pressure of the drying chamber is successively changed between atmospheric pressure and vacuum until the safety moisture is obtained. Additionally, the pressure pulsation results in the tunnel effect to enlarge and interconnect the microphones in the product, which is a benefit for moisture transfer. PVD processing creates an oxygen deficient environment which can reduce adverse biochemical reactions such as oxidation, deterioration, browning reactions, and thereby improves the product quality. PVD has been successfully employed in the drying of wolfberry and seedless grapes. So, the PVD equipment mainly consists of a heating and cooling system, vacuum generation system, vacuum creation system, and of course, the control system. All this you can see here, that is a pulse vacuum creation unit. Okay, where this is the chamber, vacuum chamber, where the product is kept, and with the help of suitable, that is, there are electric heating panel and temperature sensors, okay, pressure sensor, vacuum valve, airtight condenser, okay, electric heating panels and drain solenoid valve, and all those arrangements are provided. So, this, that is a schematic diagram of vacuum duration and atmospheric pressure duration is shown. So, this successively that material inside is brought to the low pressure, that is vacuum created, and then it is released, then vacuum created, then it is released. So, in this way you can get a better drying efficiency. Then refractance window drying, another popular method which is gaining importance, and for the drying and dehydration of fruits and vegetables, it is suitable. Okay. So, it consists of polythene tetraphthalate PET film for transmitting the radiant energy to the product for drying and to convey from one side to the another side. So, system, as you can see here in the figure schematic shown here, it consists of PET film which facilitates the transfer of heat from hot water to the product. Then it is provided with the pulleys to support the film and to convey the product. Then there is a hot water bath which heats the product. There is cold water bath which cools down the leaving product. Then water tank and heating units are provided to store and heat the water. The pump is provided to circulate water in the system, and finally the stainless steel hood here is to exhaust the vapor that is evaporated from the product. So, this is the various components which are there in the system. So, refractive window drying process parameters like water temperature. Okay. The drying rate of the product mainly depends upon the water bath temperature. Okay. And the increase in the water temperature by 10 degrees Celsius results in an increased evaporation rate by 16%. Then the product thickness. The lower thickness of the product offers better color, better flavor, better nutrient reduction and functional components. Okay. And retention of the in comparison to the high thickness. So, obviously, as in case of any drying like conventional drying also, if the product thickness is less, you will have a better efficiency. Then initial product temperature, high initial product temperature offers less drying times, less energy requirement and a high evaporation rate. Similarly, residence time, the prolonging the exposure of the products to high temperature results in poor product quality. The selection of optimum drying time is of utmost importance in order to achieve better quality products. Film thickness of the PET film, okay, being used, it influences the amount of energy radiated and conducted. So, the choice of the optimum thickness of the PET film is essential for high heat transfer and maximum mechanical strength. Then energy efficiency of the drying system, that is RF refractive window drying system typically have a thermal efficiency of around 52 to 77% and which is equivalent to the drum drying. Hot air drying system, however, delivers only 50% of the RW drying performance. Okay. Then another drying is the foam mat drying, which can be used for preparing fruits and vegetable juices, etc. Their conversion into powder. So, this can be used to prepare the powder, vegetable juice powder, fruit juice powder, etc. So, in the foam mat drying, basically that is with the help of a suitable foaming material, either it might be air, but air is avoided because it may result into the oxidation related changes. So, some foaming agent is added into the material and then it is expanded, that is it is whipped to create a foam. Okay. So, by foaming we are basically increasing the surface area of the material. Then it is spread in the form of thin sheet, okay, and put into the convective air drying system, that is air is blown and the rest is like simple air drying. So, during the heated air drying it is required to that particularly here that the foams remain stable and retain the typical open structure to simplify rapid drying and detraying, because after the there is a traying, the material which is kept, it should be there so that it can be easily, so Teflon coated belt etc. might be better suited. Okay, heat sensitive fruit juices and vegetable purees that may be hard to dry and sticky material, okay, they have been successfully dried using foam mat drying. Even we have in our laboratory we have dried tomato juice using foam mat drying technology, converted into powder. Okay. So, for that in the foam mat drying process you can see here in this you have a preparation. First thing is the preparation of the foam. So, like so if we say especially for the tomato, we take the tomato, peel it, and we can get it juice. Okay, and this tomato either by hot break method or cold break method, the juice is obtained after having a particular maybe 5 degree, 4 degree breaks. So in any fruits or vegetable, you go for the obvious treatment and get it juice. And then now with the juice, some foaming agent, that is foam producing agent like methyl cellulose, maltose, this gelatin, egg white, glycerol monostearate, etc. These are the foaming agent which can foam forming agent. Okay, they can help in the reducing the surface tension between the interfaces and help in foaming of the liquid. And then also certain stabilizing agent, that is once the foam is formed, it is necessary that it should remain in the foam form when material comes in contact with hot air. So certain agent like stabilizers like methyl cellulose, maltodextrin, etc. is added. So the stabilizing agent, foaming agent is added and whipped. So proper foaming is done. Maybe sometimes maybe 100%, 150% or 200% foaming is obtained. And then it is put into the air chamber, drying air chamber, where it may be microwave drying, hot air drying, freeze drying, whatever there. So because of the higher surface area, that is the drying rate is enhanced drying rate is. So finally you get the dried form in the form of flakes, etc. So it has to be scraped out. Sometime it has to be conditioned to introduce, like in the case of tomato powder, we have seen that once the tomato the foam, it is not very brittle, so it has to be conditioned. So introduce brittleness into it, and then by simple either by pulverizing one can make it into powder. But mind it, these are highly hygroscopic material, fruit juices, etc. So they are grinding and then finally packaging, etc. This should be taken care of in a proper manner, in a sense to that is in a environment where the moisture reabsorption of the moisture as the product is eliminated. Okay. Then osmotic drying is another. We have earlier studied the osmosis and reverse osmosis processes. Osmotic concentration we have studied. Similarly, osmotic drying can also be, there is osmotic dehydration, the phenomena of the removal of water from lower concentration of solute to higher concentration through semi-permeable. The principle is the same, but here osmotic dehydration is preferred over the other method due to the their color, aroma, nutritional constituent, flavor, etc. Their retention is better in the osmotic dehydration process. So in the particularly in the fruit, that is the certain material, this osmotic dehydration process it gives a better quality dried product. So the whole process osmotic dehydration depends upon the temperature of the osmotic solution, concentration of the osmotic solution, osmotic agents, process duration, and geometry of the food material, whether it is in the form of a thin sheet, in the form of a cube, thick cube, or fingers, etc., or whatever. So that will all. These are some of the osmotic agents which can be used. Okay, there are uses and advantages like sodium chloride. It can be used for vegetables, and here it is the high water activity depression capacity it reduces. Then sucrose, it is used, sucrose and lactose, they are mainly used for the fruits. Okay, and this sucrose particularly it reduces browning and increases retention of volatiles, and lactose there is a partial substitution of sucrose. Glycerol can be used for both fruits and vegetables, it improves texture, and a combination of the material depending upon the type of fruits and vegetables, even combination of the osmotic agents can be used, and these are adjusted according to the sensory characteristics. It combines with high water activity depression capability of the salts with high water removal capacity of the sugar, and so on. Okay. So here there is a osmotic dehydration system is shown here in the schematic. You can see there is a storage tank which is used for the preparation of the osmotic solution, and then with the help of suitable pumps and rotometer, osmotic solution is supplied into the product processing tank where the material prepared form of vegetables or fruit is put. Okay. And in this processing tank, osmotic concentration, the pump rotometer to control the flow rate, and processing tank for holding the product and osmotic solution, and finally there is here a evaporator chamber to concentrate the osmotic solution which is going, and this osmotic solution flow is again from the solution is going. So, in this way one can get osmotically dehydrated products. So, now this is the overall. So, the conclusion, the various methods we have discussed like microwave, infrared, okay, then radio frequency drying or pulse vacuum drying. So, the message which I would like to convey here, that fruits and vegetables being very sensitive, containing very sensitive components, the quality of the dried, to ensure the quality of the dried products, the advanced technologies are, that is the combination of traditional as well as advanced like microwave assisted hot air drying, microwave assisted vacuum drying, or refractive window drying, radio frequency drying, etc. Even now electrohydrodynamic drying, EHD drying, which in fact I did not cover in the lecture, but this is also coming as a very potential. It is a non-thermal process which acts on the principle of corona events, and it dries the product and gives, that is without increasing the temperature of the material much, it causes the evaporation of the moisture. So, with these are the references which are used in this. I thank you very much for your patience.